Okay, here we go. Today's Monday, April 30th. Today what we are doing, we started out by going over the answers to the acid and base strength worksheet, which the answers should be online right now. We discussed amphoteric species, autoionization of water, and Ka values, what the meaning is. Now all these things are on the final, sorry, not the final. They are on the final, but they are on the test later this week. There is a homework assignment. The worksheet is labeled Identifying Acids and Base Pairs. Okay. We're going to start out by talking about what an amphoteric species is. If you've been paying attention to what the book says, a species is not biological species. It's not like an animal. It is a specific chemical product. Okay, so HCl is a species, for instance. It's an acid species. So an amphoteric species is a species, it's a chemical, that can donate and accept protons. Now, if you remember, we were talking last week about, on Friday, about the fact that acids are the things that donate, and bases are the things that accept protons. So we've got a third class of species that are able to do both donate and accept, depending on what the situation gives them. Water, for instance, is an amphoteric species. Let me show you this. This is the equation showing how water can donate protons. Notice we've got a fairly famous weak base here, ammonia, and then we've got water. The products are ammonium and hydroxide here. If we take a close look at what's going on here, the water is actually donating protons, actually one proton in this case. So we've got the water, the acidic water is taking one of its hydrogens and giving it to NH3. The NH3 becomes NH4. The water without one of its hydrogens becomes hydroxide. Okay, so in this manner, water is donating, or water is acting as an acid. Okay. Now, in this second example, we can see that we've got hydrochloric acid, a strong acid, and we've got water, and it's forming chloride ions in the hydronium ion. In this particular case, what's happening to water is that hydrogen is staying here. The acid is known to be the one that donates the proton, or the hydrogen ion. And that's what's going on here. The hydrogen is leaving the chlorine ion, so the chlorine winds up being by itself, and it's attaching to this water. So instead of having two hydrogens, now water has three, and it's known as hydronium. So in this case, the water is acting as a base because it's accepting that hydrogen. So amphoteric species, the big idea is that they can act as both acids and bases. Okay. Are there other possibilities for amphoteric species? Sure there are. This is bicarbonate. Bicarbonates could either lose this hydrogen to become CO3 negative 2, the carbonate ion, or it could gain one to become H2CO3, and it would become, carbonic acid. Okay, notice this is acting as a base, and this is acting as an acid by losing a proton. Okay, HSO4, the bisulfate ion, if the bisulfate ion loses a proton acting as an acid, it'll become the sulfate ion, or if it acts as a base, it will become H2SO4 acid. Now you might be noticing something that's kind of weird. If it acts as an acid, it becomes a if it acts as a base, it's becoming an acid, and if it's acting as an acid, it's becoming a base because it's going to want to take on a hydrogen next. That is something that's going on, and we'll talk about that in just a moment when we talk about conjugates. H2PO4 has the same sort of options. It can become HPO4, or it can become H3PO4. Let me write that in, H3PO4, which would be phosphoric acid, or it can become HPO4 with a negative 2 charge if it lost a hydrogen. Okay. That's basically it for that. You don't need to memorize any of these. What you do need to know is that water is an amphoteric species. Okay, if you know that water is amphoteric, you will be good. Now, something interesting that goes on, since water is both an acid and a base, here's an interesting proof of what's going on. Water plus water is going to readily, since water is a weak acid, it's not strong, and it's also a weak base because we didn't tell you to memorize that it was a strong base. We got an interesting situation coming on here. This particular water here is donating a hydrogen to that water molecule, so it's becoming hydronium, while the other one is becoming hydroxide. We've got the caustic H3O plus, the caustic hydronium ion here, as well as the caustic hydroxide ion. Here we've got an acid, here we've got a base. Why is it safe to drink water? Well, it's safe to drink water because of the ratio. This is a 1-to-1 ratio. So the 1-to-1 ratio of acid to base makes it completely neutral. All right. And the interesting thing that's going on here is if we identify this as our acid because it's giving up a proton, and we identify the first water as a base because it's gaining the proton, we can also talk about the reverse reaction. We can talk about which one of these two is giving up a proton and which one's going to gain a proton. And as we pointed out here, this is the acidic components to this is the caustic component to acids. This has an extra hydrogen it can actually give up. So we're actually going to label this as our acid on this side. Now, acids on the right side are always prefaced with the word conjugate. Okay, it's the conjugate acid. It's the acid that's on the right side. That means that if this is the base over here, because it can accept a hydrogen, we're going to label it as our base, and that's going to be our conjugate base. This shouldn't be too difficult. We're going to run through this a little bit. Identifying bases and acids and conjugate bases is part of the outcomes for this chapter. We want you to be able to do that on the test. All right, so the summary of this slide, pure water does contain ions. It contains both hydronium and hydroxide ions. Those ions must be in the same concentration because if you take away one proton, you're going from one water, you're going to have to give it to another. So you're going to have a 1-to-1 ratio, which means that water is ultimately neutral. Okay, this number down here that's on the slide, we're not going to worry too much about this number until tomorrow when we start talking about doing calculations. So we'll talk about that more in depth tomorrow. Conjugate acids and bases, let's see. Summary of what we just said, every acid gives birth to a conjugate base. If we go back and we take a look, this acid has become hydroxide, which is the conjugate base. Okay, the exact opposite is true. This base, since it's accepting a hydrogen ion, is going to become a conjugate acid. Okay, so every acid gives birth to a conjugate base. Every base gives birth to a conjugate acid. So bases give birth to acids. Acids give birth to bases. Okay, we're going to skip that, and we're going to skip that. Okay. During a reaction, one molecule passes a proton to another molecule. Whatever loses the proton is an acid. Whatever accepts it is a base. That's basically what we just went over. So if we take a look at this particular reaction, what we're going to notice here is that, well, if I'm trying to identify my acid, NH3 is not an acid because acids have hydrogen written in front of them usually. I don't recognize it. Well, I should recognize it readily as a base because this is a pisser of a base. Sorry, toilet humor. Here we go. This is my acid, though. I'm going to label it as my acid because I got an extra hydrogen there, so I can label that as my acid. And it's going to give up its hydrogen to NH3, and I can see that it does. There it is, NH4. If NH3 is accepting that, then I can call NH3 my base. Now, I want to look at this other side of the reaction here to see what's going on. Identify conjugate acid and my conjugate base. Well, my conjugate acid is my thing that has a hydrogen ion that it can give up. Neither one look like an acid because neither one have a hydrogen ion written in front. If I take a look at hydroxide, if I try to take away the hydroxide's hydrogen, that would mean that all that would be left is oxygen. I don't have oxygen by itself over here, so this cannot be my acid. So I'm going to have to erase that. What I can, let me get rid of that. What I can label this as though, this hydrogen, one of those can be given to the hydroxide. If the hydroxide gets an extra hydrogen, it becomes HOH, also known as H2O, which is over here. So this looks like it's going to be my acid, and I'm going to label that as a conjugate. And this is going to be my base because it's accepting the hydrogen. And I'm going to label it as my conjugate. It helps if I can spell. I've done this only 4 times today, so. All right, there we go. And that's the basics. Identifying the pairs, well, we just did that, so we're going to skip through that. Okay, dissociation versus ionization, does it really matter? This is getting a little bit nitpicky, but here's the idea. We don't usually like to talk about acids we don't like to talk about them dissociating when they're poured into water. We like to talk about them ionizing. The reason for it is this. Dissociation is a word that applies to ionic compounds that separate into their ions. So it would apply to things like francium fluoride that have very large differences in electronegativity, as we talked about in the electronegativity chapter, in the molecular chapter at the beginning of third quarter. Ionization, on the other hand, applies to covalent compounds that become ions. Things that are much, much closer in electronegativity, like hydrogen and fluorine, are extremely close. I think the difference is like somewhere around 1.9 in electronegativity. That indicates that it's a covalent bond. So when hydrogen fluoride gets poured into water and water rips it apart, it's ripping apart a covalent compound. So since it's a covalent compound, we call it ionization instead, because it's forming ions that shouldn't necessarily be there. Okay, so we got hydrochloric, hydrobromic, and hydroiodide are covalent compounds. They share electrons instead of losing or gaining electrons. So when they get dissolved into solution, it's not that they're dissociating, they're ionizing. I'm not going to hammer that to death, so we're going to push forward here. All right, the last thing that we needed to talk about today was ionization of acids and what the K values mean. Now, if you did okay with equilibrium, this is going to make a heck of a lot of sense to you. All right, we're not going to make you guys do actual calculations of K values. What we want you to do is understand the value of K values and be able to compare 2 K values to each other, maybe 3 or 4 to each other, and give us a summary of what the K values mean. All right, K values, it's an equilibrium constant. The A stands for acids. So we've got an equilibrium constant for acids. Just like equilibrium constant values before, we don't write liquids in equilibrium constant expressions for acids. Products still go on top, so you can see here the products got written on top, and the reactants get written on the bottom. Now, I know that I said on Friday that with strong acids, these reactions go to completion. So technically, you're thinking that this should be like a 0, but it's not actually a 0 because in reality, they don't go completely to completion. You can actually draw a teeny tiny little arrow to the left. I'd say we talk about it being like 0.01% being this side and 99.99% being products. Okay, so what that means is when we write a Ka value, we don't get something over 0, so you don't get a, what do you call it? If you do anything over 0 in math in your calculator, you get a number that doesn't make sense. Your calculator tells you there's an error. But basically, here's what the idea is. If I'm trying to calculate the K value, I've got a large amount of products, an extremely small amount of reactants. I'm going to erase the 0 because it's extremely small. You can see I've written it extremely small. They're HCl. And so what we wind up with is a very large K value. These K values are always large, larger than 1 for sure, and usually we get extremely large values. Now, a typical question we might ask you is which acid is the stronger of the acids? An acid with a Ka value of 100 or an acid with a Ka value of 1? I'll give you half a moment to think about it, and you say, hey, the one with the higher number indicates a higher strength. Okay, that's right. So higher value of Ka is the higher strength. Now, if we look at weak acids, with weak acids, remember, this is a reversible reaction. Okay, again, we still don't write the water in because it's a liquid. but we do write gases and aqueous items, so they all get written in. Notice this Ka value is significantly smaller than the one on the last slide. The reason for that is because with weak acids, we usually favor the left side. So the left side has more, notice here, big, and the right side has fairly small amounts. Not a lot of products are being made. So to summarize, weak acids are going to have very small Ka values. That's because you've got a small number over a larger number. It's just fractions in math. Okay. Matter of fact, a general statement that we can make is that all weak acids are less than value of 1.00 as far as Ka values are concerned. Let's see, typical question. Which one of these is a weak acid? Well, a lot of people like to pick 1 because it's the smaller number, but the question was, which is the weak acid? This statement here says it all. They have to have a value less than 1. So which one has a weak acid? Neither of these is a weak acid. In order to be a weak acid, you got to be less than 1. So maybe this is a weak acid. Okay, I'd pick that one. All right, I think that's about it. So